Gamers, it's gaming time. It's gaming time. I've got wheat in my ears as well, so it's confusing. Anyway. Welcome. I'm gonna go talk to wheat in like a second. But we're back. It's science time. Today, I don't know what wheat's got ready, but I looked at limits again to refresh what limits are, so that's good. That's good. And it's gonna be fun. I'm excited. I'm excited. So yeah, let's just get pogging, you know? Let's get pogging, as they say. We're going back to Japanese city pop and funk, because that's my favorite playlist to listen to recently on stream. Because it's nice. Let's see what Wheat is up to. Bello. Loving the high quality notes here, as is tradition. Of course, no, it doesn't. I heard you like, I think I heard you like open a door. That was like, yeah, that was about it. Oh, I forgot, I've got the wrong pen. There's got to be a better way, right? Yeah. Like, I don't know how it just keeps dying on you. But even if, like, when you're writing notes on it, it, like, stops being high quality, you know?
Container, a wooden bowl, a plastic
water Champ's doing math in my chat. I'm scared.
Rechamp just resubscribed for 14 months. 14 months? That's like 5 plus 9 months. That's like 7 times 7 months. That's like 3 cube root of 2744 months. That's like int liggen streepje 2 pi dakje pi 7 sin left x right dx months. That's like 3 oneindig k is min 1 1 tweede dakje k. Plus lambda fx months.
What? Who are you talking to? Oh, I see. Hello, Artafki as well, and hello, Champ. Thank you for the resub. Boom. We're on. Okay. Sure. I mean, yeah. If you're actually getting marked for it. Wheat is mute. Has Wheat been mute this whole time and no one's been fucking telling me? I can't believe this.
Nice. We might talk about vaguely similar concepts that perhaps may aid me in some answers, but that's allowed because that's just me like working shit out, you know? Maybe we'll substitute in some numbers. Well, actually, we can't just substitute in some numbers because the questions aren't like that, so that wouldn't work at all. But we'll do something that makes sense, you know?
Sure.
Fortunately,
what is it
the topic which I said...
About?
Well, the topic that I said we were going to talk about today, first for cosmology at the very least, was the FLRW metric, which also happens to be what the next question of my assignment is on. So
FLRW.
Yes.
Metric. Okay, I'm writing it down. It's on your face now. You'll appreciate that.
Always. So let me just grab what I'm going to need for this, because I think that
How did I do
talking
this last
about
time?
like workshop questions, probably not that interesting. So I'm not going to do that again. We're just going to talk about the topics themselves this time, and
Yeah.
go through them in a more similar way to how we did on Uncertainly Accurate, rather than
Yeah.
maths.
That's how it always goes, Artafki.
So I
Lingus,
have
Ringus, Wingus metric. True, yeah, that's what it stands for, actually. You're so right.
true. Sorry, I'm just scribbling to stop it losing quality. I just need to find like the actual notes on this. I mean, I could go to my notes, I suppose, but we can do better than that, right?
Could we?
Yeah,
Sure.
they're not kept where you would expect, because the notes for this module are all encompassing. So they're just all in one big note file, rather than split up into weeks or whatever. So now I have to find the page, which I'm pretty sure is page 28. Or we can just talk about it in a more generic way, of course. I mean, there is maybe some background knowledge that we should do. Probably quite
Yeah.
important.
Sure.
Yeah,
Like?
there's a whole section on it. And apparently that's important if I'm not taking general relativity, which I'm not.
What is the background knowledge part?
Well, it's just titled towards the metric of the universe, so it's to do that. So the FLRW metric is the metric of the universe. The section that comes before that goes into how we get there, and the quality's gone. Whatever.
Yeah.
Fuck's sake.
Can you not just like bring it back?
No.
Take it back now, y'all.
I can't. I don't know why.
It's so stupid.
It is so stupid. Do I not even have...
Take it back now, y'all.
Where's the Redox and
One
Wheater's
top this
Uncertainly
time.
Accurate saved image? Because I want to get that up.
Which one?
The one that I put on Twitter. It's meant to be saved in here somewhere, but I can't see it.
You put one on Twitter?
Last week. That's not it. I had a
You ever order
stick in
something
my
on
quality
Delivery food thing, and the delivery man never shows, and you're like, he clearly doesn't know how to read signs, and now I need to get it reordered again, and the service, for some reason, assigns the same delivery man to deliver the replacement that he couldn't deliver the first time. No? No, actually. I've never done that. But also, that is quite funny.
I just didn't have a button I can press.
What did he do with the first order? That's what? Like, surely they must recognize that, like, he says he delivered it.
That's close.
Very, very strange. Very, very strange.
Right, anyway. We're back. Like, what I can do is actually, because this is just like an app on Chrome, I could just put it up, but it doesn't update in real time. So, like, I could just go to my login screen for this on my other PC and just be like, oh, look at that, isn't that nice? But it wouldn't really work.
I'm sure there's better ways to just link your Chromebook to your...
Well, maybe there are, but I don't fucking know what they are. Like, it wants me to download extensions and shit when I Googled it, which I don't want to fucking do. Why would I do that?
On your Chromebook, at the bottom right, select the time settings. On the left, select connected devices. Next to nearby share, select setup. Choose a name for your device and select done. Select your device visibility. Choose your options. Select confirm. That's what Google says when I Google it.
My device visibility, you say? Hang on, where was this? Settings?
Yeah, time settings, apparently.
Search
Select the
settings. Visibility.
Any exclamation mark admins in the chat?
Nothing fucking comes up. Accessibility is the most similar. That's not what we want. I imagine it's on Bluetooth.
At the bottom
no.
right, you select time, and then there's a little arrow settings. On the left, select connected devices.
Yeah.
And then go to nearby share, select setup,
On it.
choose a name for your device and select done.
Sure. On.
And select device visibility.
Change visibility.
Choose your options.
Um,
Uh,
all contacts? Does that include me? So, hang on, because I did something similar to this on my other PC. Because I was trying to get it to fucking work. And failing. Where did I do that?
I don't know. You could do that,
Share.
Champ. Champ has sent me a very beautiful video of a baby.
The fuck's that got to do with anything?
Nothing. I just saw it right now and I was hulking. I'll just link you the support file
Sure.
instead of reading it through for you.
I can't fucking open it there. Right. That's share files. That's not what I want to do. I want to share my screen.
Listen, I looked up Chromebook shared to PC. I didn't read the title. Okay. That
Great.
doesn't help. Okay. Listen.
Okay, this is as
Chrome
good as it
remote
gets.
desktop.
I'm afraid.
No, that's not either.
The thing is, like, it's showing a particularly bad view at the moment. I'm not even streaming my screen. So.
How? There has to be a way.
Oh, fuck, I still was. Oh, I see. There's a stop button that's separate to the one in Discord, so it just stopped showing updates to it. It gradually got worse. So I can bring up that, right? Oh,
Oh God.
come back.
That account as Discord in white blind mode.
Yeah, I know, it's fucking horrible. So I can bring up that, and then I have my
Voice.
options, which are just voice settings and shit. Like, woohoo. That's no good. I've muted that, I hope.
Okay.
Noise suppression. Turn that off. Let's turn echo cancellation off, just in case these are messing with things. Automatic gain control off. Nice. I'll keep auto sensitivity, of course. Maybe that will improve it. Who fucking knows? Yeah, that's all I can do. I can't do anything about the stream quality itself.
That's very weird. I mean, so far it looks good. Just never stop drawing, I guess.
Well, I tried that and it still got worse. I was scribbling that entire time I was talking before.
Really?
Anyway. So, let me
Okay.
just pull up some shit for the FLDR metric.
Yeah.
Is
Yeah.
that even what it's called? I mean, FLRW, not FLDR.
Yeah, faster than light whatever.
I just need to find something I wrote earlier. Here we go. This is something I wrote earlier.
Here's one I wrote earlier.
Here's one I wrote earlier. This was actually for a workshop question.
God.
I didn't get the right answer here because I went about it a completely wrong way, but it's a useful barometer for what's happening. So let me go get the actual equation up though, because that would make far more sense, wouldn't it?
It would make sense. Maybe just like
there we go.
The definition of what it is. 3 equations to
for fuck's sake.
To
you
go
see, it's not
between, is that what it said?
It's got nothing to do with what I'm doing.
No, it just dies after a while. I don't know why. It's very strange.
I can't even go back to fucking Discord now because I've
opened
my settings.
Give your other account
Nitro.
Yeah, it's the only way.
Fuck's sake. We'll see, okay?
Has to be a better way to do this.
I'm sure. Well, we're in a science stream, so hopefully someone can figure it out.
Any sciences in the chat who can figure it out?
So there we go. If I don't touch anything, who knows? Maybe it will stay fine. Maybe it's the motion that's thrown off. So these are the 3 possible equations for FLRW.
What is
FLWR as I've written here? So fuck knows what order the names go in.
What does it mean? Can you tell us that?
So FLWR is the names of 4 scientists who developed this. What it is essentially the metric of the universe. And well, what does it mean?
Friedman, Lemaitre, Robertson, Walker metric. There we
Yeah,
go.
what a
So is
multinational group of
RW.
people. So
Okay.
all it is basically is a spatial geometry equation. So like each of the terms is a different coordinate measurement for how that is gradiented. So if you consider it as like a three-dimensional shape, all this equation is doing is saying what shape that is. One of these equations, the top one, number one, is if the universe is flat. That's not right, actually. That's not how that works. Is that how that works? That's not how that works. No, that's termed up. Okay, that's something completely different. So essentially, these equations do that. And then what happens is you have this k value in the third equation. So the first equation is how it comes out, and you can write that in a few forms. And then as you were to expand the r values within this, it would kind of throw things off a bit. So they simplify it by substituting in a k value later on, which is down here. And that k value, this one, that was a rubber. This one is simply valued to +1, -1, or 0. And that determines whether it's curved positively, which would mean it's essentially a sphere, is flat, which would mean it's an endlessly extending plane, or is negatively curved, in which case you can't visualize it because you can't. No one knows what negatively curved space would look like as a real shape because there isn't a real shape that is negatively curved. So that's what it is. Okay, it's got lots of interesting things about it. In that they went through a lot of interesting maths to get to the point where they could unify it. Because to begin with, the problem with these equations to begin with was that you could geometrically shape the universe as three different systems, but you couldn't unify it. And that's what they ended up doing amongst finding the original equation in the first place. They did all of it basically. And that last one, number 3, is the equation that they used for it.
We've lost quality.
It's very interesting. Fuck's sake. Can I just if I go into my thing, how does it look on the Discord stream for you? Is it?
It looks
the stream
same.
from the
Yeah, it looks. Shit.
Okay, so it's the stream. It's the stream from the tablet, not the stream that I'm
yeah.
watching.
Did you see they're renaming the Drake equation to the Millie Bobby Brown equation?
Nice.
Fuck. Why would they do that? She's literally homophobic, guys. The fuck?
So we should probably talk about what we mean by saying a flat, curved, negatively curved space.
Yeah.
Because that's interesting and isn't actually something that we really talked about. So it'll be interesting for me to go through that as well.
Okay.
Now we're very much in uncertainty accurate territory where
we're back in the olden days.
We have to look things up.
No, this is great.
Because essentially what I've had to do with this equation and what I will be doing in my assignment is I'm given basically variations of it and asked to determine whether this would be I have to determine whether the metric that I'm given as the equation would be isometric and homogeneous, as we've spoken about last week, and then whether or not it would be flat, if it would be isometric and homogeneous. So I'm not quite certain how to do that quite yet. The quality's gone again. It is definitely determined on how much I'm doing on this screen. If I just leave it, it goes. Fortunately, we don't really need this right now, so whatever. You can have a blurred picture.
Sure.
So, yeah, my assignment is to look into all of that goodness, whether various equations of this format would be isometric and homogeneous, and whether or not they would be flat, I think. So if by the end of this section we are able to answer a range of those equations, excuse me, we're in a great shape. Did I leave my? No, I got my drink here.
Okay.
So, what is? Oh yeah, there's you've got the general metric up. Maybe I should do that too. Hang on,
Yeah, I've just got the Wikipedia
I've
page
had a
open.
brilliant idea. Check. Okay, here we go. Let me hang on a sec. Duplicate this. This is now science redox.
I'm scared. I don't
And
know what's going on.
I'll move that up to there. And then on this screen, right, check this out. I'm not done yet. Hang on.
What,
Oh,
you're just gonna show my screen? For
oh,
fuck's
it's a
sake.
switched view. It's
Fuck's
fucking
sake.
genius.
Okay.
And also,
Incredible.
like, mine's actually more readable like that.
True!
because
That is true, actually.
because it stops fucking up the quality. So, well, it doesn't. It keeps the quality fucked up.
It's so
But
fucked up, but at that size, the quality was bad anyway.
yeah,
Yeah.
I'm a genius. Right.
So,
Anyway.
I think when I was looking at it, I think which one was it? Like this was pretty similar to what you had, but not.
I think that's so. There are different
But yeah,
notations for this that mean
yeah, I
vaguely the
think
same
that's the
thing.
point. Because you don't have a single sigma in yours, I think. If I...
No, I'm not quite sure what that's doing there.
But these don't have S's
Oh,
and you have S's, so I think
oh
you
wait,
just
hang on.
wrote
The
a
second
sigma
one
as S.
down.
Yeah.
In reduced circumference polar coordinates.
Yeah, you've
That
got
looks
some
more
different
similar to what I know.
coordinates ones. You've got hyperspherical coordinates and then Cartesian down here, which is just okay.
Yeah, so the one that we deal with is the one above that, the reduced circumference polar coordinates, because that's the one I'm familiar with, the dr squared over 1 minus kr squared. That's the third equation that I was showing before.
So basically, just generally a metric is what we should actually talk about, right?
Yeah.
Oh God, what is this? This is not what I went to look for. Why is this not linked to the word metric? Okay, wait, we're doing some magic.
I'm trying to find my shit notes about this.
Here we go. A
Oh, I
metric.
found our picture. There we go. That'll do.
Oh, there it is. Beautiful. Science with and 7 p.m. BSc. Beautiful. Mathematic.
Don't dead open inside. It's all part of it, you know. What the fuck are you talking about, Wise?
Do you play FNAF?
Don't know what that is.
What do you mean you don't know what that is? You know what FNAF is.
No, I don't.
What? Yes, you do. Come on now.
Friday Night at Freddy's, is it that?
Friday Night at Freddy's. Damn, me and the gays having a Friday Night at Freddy's. Damn. I bet Freddy get freaky. I bet. I bet. Thank you for adding the quote, Wise. So basically, a metric is a way of writing down like coordinates and changing between coordinates, right? Is that what am I correct when I say that?
Yeah.
Yeah. So it's a way of having different kinds of coordinates. So for example, let's just talk about the basic ones. So the very standard way of writing down coordinates is God, that's very thick. Very thick. Is like this. Like let's say you have this, that one, and then you have one that's on here. There you go. So that's the way you could have space, right? Which one is which one usually? I just want to know what the standard is. I think it's like this one's X, this one's Y, and that one's Z. I think.
Yeah, Z is depth, I think. And oh no, so not what you've drawn. I would tend to treat Z as depth and Y as height because its X and Y remain the same as they would in 2D.
Yeah, but I think they don't.
Maybe. It doesn't make a difference, though.
Well, I mean,
Where you
there's
could
like
just rotate the
left-handedness and
graph, so
right-handedness, but
you
yeah.
could just rotate it. So
Well, yeah, but there's left and right-handedness. Um,
yeah, one would go the other way. Who cares? It's fine.
yeah, but whatever. It doesn't really matter. Um, so yeah, you this. So let's say we have a point in space that's right here, and we want to mark that point mathematically. We have to look at the coordinates, right? So let's say the x coordinate. It's hello. It's
Hello.
this height. Well, it's not x. It's this far. So that's the x coordinate. We have a certain x. Let's do a capital. Let's see the on the y coordinate. It's like this far, this direction. So we get a certain y. There we go. And then on the z direction, we get a certain height like that. And those coordinates give us a way to describe this point, right? Which this is a very simple way of doing it. This is the basic one. Everyone will understand this.
Mm-hmm.
But sometimes this is not the most useful way of representing that point. Sometimes this can give us a lot of confusing and long mathematical equations and stuff. And it might be easier to represent those points as, like, for example, spherical coordinates. And to change to spherical coordinates, to a spherical coordinate system, instead of x, y, z, that's well, you still have z. You still have z, but you use instead of x and y, you use these two. Let me get some colors. You'd use the angle from the z, like this. Boom, this angle, which is phi. It's cylindrical. Yeah, I'm looking at the wrong one. You're right. You're right. You're right. I was looking at the wrong one. Spherical is the distance r. So you get that one. You get I need more colors. You get this angle. I think, yeah, you'd get this angle. Which is theta, and then you have one non-angular one that is this distance. We've already done green. There's not enough colors in the world. Here you go. There's this distance. Let's just assume the point is actually here, which is r, which is a vector. Well, it's not a vector. It's just a length. And that is another way of representing these coordinates, this point in space. Which is all very fun to just say like that, but it can get a bit confusing. Because, like, how are we gonna do this? Let's say this point is the point 1, 1, 1. How would we write it in these angles? So we need some way of going from this to this, and that's where the metric comes in. And, like, the metric is the way to go between the two, right?
Yeah.
And so we get these equations to find these things. And that's why you have a whole bunch of different ones, like we were looking at earlier, I think.
Yeah.
Let's look at this. So you've got a bunch of different ones. Like if you want to write this metric of whatever it uses, you need to write it as, for example, polar coordinates. So we have phi, we have theta, and we have r here. And then, yeah, okay, it's just a bit confusing. So basically, it's just a way of writing coordinates in a different way, and that makes a lot of equations and stuff simpler because we just have it easier. It makes it simpler because let's say this is hard without like specific examples. Um, let's say like a
Well,
spherical.
here's a
Let's get
specific
a specific
example.
one.
um, so in the case of the FLRW metric, essentially what you're doing is tracking the positions in the XYZ coordinates as time progresses. So that's why the equation contains the dt thing, whatever that is, a change of time, and it's why the function itself has the s bracket t part of it, which is sometimes replaced by at. They're slightly different, but essentially at any given point, it's tracking as time changes. Here's how the function changes at different times, and that's how you find your positions. Very interesting.
Yeah, it's just like a standard thing. Yeah, it's just sometimes it's easier if you're working with a system that is symmetrical in like spherical directions or stuff like that. It makes it easier because you lose a lot of like annoying. Oh, I'm writing the wrong one down. Well, this still works, but this is like in one direction. For example, if you want to get r, this is how you'd get this distance r, right? Because it's this distance. This is just Pythagoras, basically. And then there's different ways to do this. And then after a lot of annoying work, you can see the other direction is like this. Theta cosine phi, and then we've got y is very similar, but with a sine, and then z is r cosine, because the other one becomes annoying. He did. He literally did. He literally did wise. But yeah, so let's say, well, let's say we know its location in spherical coordinates. So let's say we have a point and we can represent the point as 1 pi pi over 2. Right? That's very simple to just fill in because we know those. Turns out law of sins is the new Pythagoras. Oh, I see. I was like, what are you saying? So we just fill those in, right? One is the r. This one's the theta. This one's the phi. So we can just easily transform these into the x would be 1. The sine of pi is, God, I need a unit circle. Sine of pi is 0. So boom, we get 0. We get 0 for y as well, and then for z we get the cosine of pi, which is -1, -1. So boom. This is the point that we represent as z1. So let's say this is the point 1. Boom. As that point represented both in polar coordinates and in normal Cartesian coordinates, as we call it. God, didn't expect to be talking about Cartesian coordinates.
Nice.
But here we are. So this is the basic shit, and then we can go into more annoying shit. Question, yes. I'm waiting. Everyone's quiet, waiting for you, champ. Come on. No, I can't.
Not possible. Not possible. I could maybe do it to myself, but why would I?
Yeah.
I don't gain anything.
Wizard. But yeah, and then this is just a different, like, this is an example where we use polar coordinates and Cartesian, but we uses this new one, which is whatever the fuck it was called, our FLRW metric, which is
Indeed.
to help figure out the shape of space-time, or whatever you were saying.
Indeed.
Continue.
So this is where all these lovely three equations come in, which are somewhere in my vague array of drawings. Christ. Oh, it was meant to be right next to that one. Did I accidentally edit it? Okay, there it is. Bam. Isn't that lovely?
Yeah. Very legible.
Yeah. Oh, for goodness sake. It was fine for the entire time you were talking.
I don't know how it does that. Is it because I'm looking at it? Do I need to stop looking at it?
I don't
If
know.
I just close my eyes. Should I write them down?
There they are. You can if you want. It might take a while.
Yeah, while you talk, I'll just write them down.
Sure. So, yeah, we have 3 possible geometries. We actually have a nice drawing of this, which would be nice if I could get on the screen, but unfortunately I can't. Hang on. I'll get it up briefly so you can see it, and then I'll hide it. Wow, look at that. Hang on. Wow. There they are.
If you can, I mean, you can get it on screen. I'm looking at your Discord, so
It's not on Discord.
yeah, exactly. So
Wow, aren't they fucking great?
You can, just keep it up there.
These are the spatial
I'm writing
geometries that we
these.
could have. Isn't that lovely? It's great. Oh, that's interesting. So the spatial geometry is decided by the value of omega. I will remember that when I have to do the assignment. So that's nice. Where was I? Where's it? Oh fuck!
Wait, that's
my
not a
notes.
V.
I
That's
need
an
those.
R.
Hang on, I need those back. I need that back. Where'd it go?
Where'd what go?
I closed my notes rather than move them back to the tab I was reading them in.
I can literally see the notes still.
What are you talking about?
I'm still writing them.
Oh, not the ones I've got written down. I mean the ones I'm reading from.
Oh, I see. They're different notes.
I briefly got up a picture of a 3D representation of the geometries.
Well, I'll have to trust your word on it. Because I did not see it. And then the last one is minus c squared dt squared plus s squared of t, which we've already had a lot of time. Can we talk about Champ's load collector? No.
No.
If Champ wants to talk about the load collector, he can get his own fucking science show, bitch. Is this a different... Okay. What happened here in the last step? Can we talk about that?
The last step. I can... Yeah.
Yeah, can we just, like, talk about these equations a bit?
Sure, we'll talk about the equivalence of them. So, if I go to this one. So, here they are represented as matrices in very low quality. Fuck's sake.
I'll have to squeeze my eyes a bit.
They are represented in matrices without the k value of them all. Let me get it in a place where I can actually see it. And I'll go back to science view, so my view's big. I'm a fucking genius. So what happens at each stage is that it's essentially just a replacement. So each of these equations have slightly different entries for them, particularly the first term of the bracket. So in the top one, dr squared, in the second one, dr squared over 1 minus kr squared r squared, and in the third one, dr squared over 1 minus k r squared, which is essentially just k. It's a representation of r as k. It's kappa, actually. It's not a k, it's kappa. I thought that was interesting. It's kappa. So if you want to type kappa, type kappa. Um,
Kappa is a Greek. It's a Greek letter, which
yeah.
is not very useful in maths because it's literally just a K.
Hmm.
Like it's basically the same symbol. Unlike like things like alpha and stuff where you have like it's actually different. But no, kappa's just a K.
Sorry, I'm just getting my head back around this proof.
Yeah, I can't see anything. What are you doing? We're talking about the cosmology FLRW matrix, not matrix, metric. But
Yeah,
we is looking at a metric.
matrix.
If you want to see what, yeah, matrix. I did it wrong. If you want to see what we over there is doing, go and look at the thing that just posted in chat. Wait, chat is also over there for you. Go and look at the chat over there. And
Oh, the quality's gone again. For fuck's sake.
yeah.
Yeah. Good luck seeing anything I'm doing though, because it
So
all fucking breaks.
okay, can we just like talk about these? So how do you, from here to here, why does this just happen? What is the differences between these three?
So,
Because like
there.
obviously the only real difference
So
that I
essentially,
see is this
the
part.
problem is that the first one isn't unified. So the first one won't work in, well, or rather, it will be a different equation depending on the curvature of, well, space time. So the second
Okay.
and third equations are there to resolve that by substituting in this value for k in place of r. And to do that, it does this maths, okay? So in a closed curvature, so essentially a sphere, what
Mhm.
you have, what gets substituted in for the value of r there is sine of x for the x coordinate of what's happening. And so if you do some maths, you essentially find out what dr by dx squared is, so differentiate it twice, and that comes out to 1 minus sine x squared, which is 1 minus
Which
r
is
squared.
r squared. Yeah. Okay.
Similarly, in a flat universe where kappa would be 0, you have r equal to x because it's uniform, nice and straight, nice and flat, doesn't go anywhere. So dr by dx is 1, and dr by dx squared is also 1. Second differential of it, second derivative, I should say. Similarly, in an open universe where it curves negatively, so the saddle quotations view, you do essentially the same thing. You just go r, differentiate it twice, get to 1 plus sine x squared, which is 1 plus r squared. And then from
Yeah, but that's
there,
the hyperbolic sign instead of the normal sign.
yeah, sine, hyperbolic sine of that squared.
Mhm.
So then you go through and substitute in at every point along that equation. So except the ds squared. So c squared by dt squared doesn't include an r, so nothing changes for it.
Yeah. So you
Within
only
the bracket,
replace it in the ones with the r.
yeah, which is fortunately only the second part of the equation.
Oh yeah. This is different. I didn't realize this.
So yeah, there it is as matrix form, which is not technically correct. You'd actually write that as a 3 by 3, but whatever. But as you go through it, excuse me. So okay, yeah, and then what you have in addition, is that each of those equations can then be linked to each other by applying a value to k. So the last step of those 3 points is that you set dr squared by dx squared equal to, the second derivative of r by x to 1 to equal 1 minus kr squared, or kappa r
that's a
squared.
second derivative. Oh yeah. Okay.
Yeah, because what you have here is one is 1 minus r squared, another one is just 1, and the other is 1 plus r squared. So the only thing that's changing is by how much you're taking away from kr squared or adding it. So if you set that to, so if you set k to plus 1, minus 1, or 0, you've essentially got all three of those equations in one, because you would have, if k was 0, it would be 1. If k was plus 1, it would, oh, fuck's sake. If k was +1, it would be 1 plus r squared, and if k was -1, it would fucking hell. I just stop it. You stupid. Oh, fucking hell. What have I done? Oh, you have to drag it. Ah! No. Come back.
This is great.
And if k was -1, you get the 1 minus r squared. So you can easily just jump between them by giving yourself a value for kappa.
Still loading.
Why is it not coming up now? Oh my god.
Wait, that doesn't... I don't think he has wise.
I've not done this
Oh
before.
my god.
Look, I can't be blamed
So,
for this shit.
okay, I still don't get what is the difference between the first and the second. Like, how do you get there? Also, why did I write this R in brackets? What was that? Because this R in brackets becomes R squared.
I'm not sure why you
And
did do
here, I don't know, that's just what you had.
that. I've lost all control. This is a fucking nightmare.
This is incredible.
I feel like Discord's crashed now on my tablet.
Of course. Disconnect
Hang
and
on.
reconnect?
Can I just need to fucking hell. I need to close the fucking thing first. I can't, like... Okay, it's closed. Brilliant. Now open. Stop sharing. You twat. I can't do it. Exit call? I can't do that either. I can't press a single button in Discord. Close.
Just
Okay, it's closed.
entirely close Discord, yeah.
In theory. Now open Discord.
Well, it's not closed, is it?
It's not opening.
Incredible.
Like I presume my screen isn't sharing because I
No,
can't see it right now.
it's
Okay,
just
Discord
showing-
is showing me the nice reset screen right now.
Yeah.
So that's lovely.
Oh, now the
Brilliant.
stream's ended.
Brilliant. It's done shit. Great. Am I even in the call on this? No, I'm not.
You are according to Discord.
Yes,
my
I am,
side.
but I can't edit anything. So
Oh,
I've
there you
left
go.
the call.
Now I can hear you twice. You're back.
Okay, now I've muted on that. I'm back.
Okay.
Open this, share screen.
It's happening. It's all happening. Oh. Beautiful.
You say that. Jesus fucking Christ, no it isn't. Right.
Okay.
So what you've done
is KR?
is substituted in dr by dx squared. So you have that value there. Dr by x squared is 1 minus k r squared. And what you had originally, somewhere in the equation, which I didn't really show, which is probably why I didn't get this answer right, is that then you put that in where that was. So you have dr squared there, and then you just be like, okay, well, we'll rearrange this a little bit somehow. Effectively, that gets substituted in. So rather than dr squared, you put it as dr squared over that. I imagine you rearrange it so the dx squared gets put on the other side of it or something, and then you divide it by 1 minus kr squared.
Is this just all using this third? I'm still not entirely sure why this is happening. What is the difference between these three they had originally?
Nothing. It's just a substitution of this k value into the equation using this property of what's happened to r. Because in the full expansion of the first equation, that r is sine of x. Well, it depends on the geometry. In one case, in a closed universe, so a sphere, it's sine of x. In a flat universe, it's x. And in a open universe, it's a hyperbolic sine of x. So all you're doing by substituting in this k value is essentially putting a link between all of those using a k value rather than any kind of different.
Let's see. Wait, what is d omega again?
D omega
omega?
is
I feel like that.
sine of x, sine of theta.
Okay, so
Yeah. So that we leave alone, because we can. For there is no r within that equation. There was this. This was a workshop question, so it's been actually answered by professionals. So I could just read that. Give me a sec. I'll get it up. It's the same idea, but there's probably a big linking factor that I'm just gonna say out loud, and it's gonna be great.
That'll be it.
Exercise 2 solutions. There we go. Bam. Okay. I'm just gonna write that shit out. So.
Okay.
So you have the equation that you've written there.
Yeah.
Which is
so top one is what you get first, but it's a bit annoying, so we try to get it. We try to unify
sorry,
it.
I was wrong about what d omega is. It might be that as well, but in the case of the written notes, d omega squared equals d theta plus theta. Oh, sorry, that's squared. D theta squared plus theta squared d phi squared.
Okay.
And from there, in flat space, all three metrics are the same. Great, that's fine. So I'll just read out what the question was to begin with. The space-time geometry of the universe is described by the FLRW metric on large scales, so it's an important item in cosmology. Explicitly show how you can go between the three forms of this metric given in the lectures by making coordinate transformations. Show this for each of the three types of geometry. Whatever. The answer for flat space is just they're all the same. So there was no written answer for that.
In flat space, they all work the same. Yeah, because you said in flat space, KR is 0, right? That's what you said, right? So yeah, if KR is 0, then they all just become the top one again. Because then this is just 1. Well, except, I guess, is this just r squared as well? I don't know why. That's the only part that confuses me. Is this just r squared as well up here?
I think that's actually, no, that's a function of it, I think. I think that's meant to be, so that's, I think, meant to be written as what I've just written there, SK of R.
I see.
Where's the picture? Fucking hell.
What picture?
View? My picture.
I don't know.
Oh, fuck's sake, it didn't. There it is. Okay, I've got it back.
Oh, I see.
Yeah, lovely. SK. SK
The
of R.
quality's gone
Bam.
again.
Oh, it went as soon as I opened the damn
Literally,
thing.
as soon as
if I just don't look at it, if I just
maybe it'll
pretend,
come back. Oh.
No, it doesn't come back. If it came back, I wouldn't have this problem.
I don't understand the quality just leaving.
I don't understand why it doesn't come back more than anything. Like, that's what... Like, I'm fine with it dropping, but it should come back, but it doesn't. Anyway. So from there, we have... Let's give R sine R over R. If K equals +1. R. If K equals 0 and R hyperbolic sine R over R if K equals -1, which is essentially all that we've been substituting in for there.
Yeah. Okay.
So from there, seeing as we know that, we go from... I'm going to zoom in a bit so I don't take up so much space because I've got to be right. The original equation, which is ds squared equal to -c squared dt squared plus function of time squared brackets dr squared plus a function by k of r d omega squared. Bam. Which is the same thing. I think that was a bit missing from the original one. No, that is what you got. Okay. Now, of course, after I've corrected. Don't know where it was originally. And so from there, using this bit, this sk of r, we go quite easily to ds squared equals minus c squared dt squared plus s squared of t. So the dr gets some substitution. So that becomes dr squared over 1 minus k r prime squared, which is unhelpful because it's very unclear what it means by that. But essentially, this is r once it's had... Oh, right, no, that's just... Of course, that's dr by dx. Right, okay, that reminds me of the big problem with this, okay? This is why things get confusing. It is not the same thing in the later equations as it was in the originals. It's actually the differential of them.
Yeah, I was gonna say if you do like
yeah,
prime or whatever you call it, like accent as I'd call it, that's just the
yeah, it's
differential to
somewhat
t.
unhelpful over
Dot is usually the one to x, I
squared.
think. Or is it the other way around? No, I think that is true. Or to r.
Bam.
Okay, so that's not what I have here, right?
I imagine there's more steps.
Well,
so
no,
that
is
exactly
that's the
second one.
second one, but
Yeah.
with these added.
Yes. Yeah, it's a very confusing thing because a lot
It's a
of the notation for these have r meaning the same as r, and they don't put the primes in there. So it doesn't do r prime, even though it probably should. And
but these are the differential, like the derivative of r, right? To the derivative to
yeah,
t.
with respect to time.
Yeah.
So when I was doing dr by dx in the previous ones, those could also be dr by dt. It just depends how, because everyone seems to use different notation for this, and it means the same thing. The example I was using when I was answering that question was using dr by dx, which is the same in this version as using dr by dt.
Is it? Because...
Yes.
Sure.
I know, it's unhelpful, but they're the same.
Sure.
Because it's the same substitution, effectively.
Yeah, but if you've already got t in here, and r is dependent of t, then it makes sense that you use that it's dt and not dx.
Whatever. The last step of this is to rescale the k value by r squared, which just means that you include the over r squared bit in the k itself. So you get rid of it like that.
What? So you just say that this new
you just
KR
say that k
is
equals
the first one.
K over r squared, and that's it. And then you just substitute it back in like that.
I see. And then nothing. Is this also a differential, by the way?
Which bit?
This r. Just
capital R.
No, the small one. Is this one in the third equation? Is what I'm talking about.
No.
These are not differential. Okay.
No.
Derivatives even.
They probably are, but but in the notation here, no, they're not. Even though the ones in the above one were.
So, but through that substitution, they become not though. Okay, that makes sense.
Yeah.
So we just say that kappa r squared is kappa r derivative squared r squared, and then through that we probably find that the derivative of r squared is the same as r squared. I'm assuming.
Mayhaps we do. I don't see why we would, but oh no, yeah, of course we do, because we've rescaled it by... Hang on, maybe the next sentence says something. No, it doesn't. it just mentions that there is no common convention about which choice of K or kappa to use. Indeed, there are no common conventions for any of these letters to use. Has that been blank that entire time on my screen? Why can I not see anything?
I don't know. I can see what you're writing.
Oh no, I can. Why does it disappear when I look at it? It only disappears when I look at it, and that's it. It's fine. It's fine. Okay.
How strange.
I'm trying very hard not to. Now it's gone. Now it's back. Now it's still there. Sorry, I'm doing some testing. Now it's gone. Now it's gone.
Okay, so now we've looked at
Now it's back.
what. So this is the way to describe coming from these what was it? Spherical. No, which one were it? Let me have a look. Reduce circumference polar coordinates.
Yeah,
That's
this
where
is
you
how you
come from.
unify it so that it works.
And we've just unified it.
Yeah,
Yeah.
in all different systems. You can see the thing down at the bottom. Although they've described it differently using hyperspherical coordinates, which I haven't done. Which interesting to see in those. That the function of K by R is
Hyperspherical or
slightly different.
curvature normalized coordinates.
Interesting.
The coordinate r is proportional to the radial distance. So yeah, also they use sigma instead of s. And they use so r squared. Sure, whatever.
Oh, I think that makes sense actually, because these are like
Yeah, it's this part.
slight. I'm going to use the term slightly curved, where they've said greater than or less than 0. Interestingly, the universe as we observe it is flat. However, the error bars on that, because unless you get exactly 0 as a result in this equation, you can't say for certain it's flat, and the error bars on it will mean that we can never measure it as exactly flat. So something that will be never confirmed, despite it being practically notable, is that the universe is flat. Treat it like how much
These
of
goddamn
the
flat universers these days. Can't
yeah.
believe it.
Think about it, like how much of the Earth would you need to look at to measure that it's not flat?
Yeah, well,
And-
that's while it's literally flat Earth. Well, on the Earth, it feels like it's flat,
Yeah.
and
So
the universe is way, way bigger. So even if it was a sphere and we're standing on it, it's
yeah, we
so
might
hard
not
to
have
tell
enough.
because we're like little. It's as if like an atom on the Earth.
Yeah, I mean,
it's so flat.
we have the entirety of the observable universe to go by. However, we don't know how big the rest of the universe is.
Yeah, we don't know how much of the what percentage of the entire universe that is.
Yeah, like there are estimates for which, if you were to base it off of that, you would certainly say that, because I'm pretty sure based on those, the observable universe is about a quarter of the entire universe. However, like that is kind of more like the universe resulting from the Big Bang, not necessarily anything else that could be beyond the observable universe, i.e., what the universe is expanding into. That we don't know.
But it's not expanding into anything.
No, but does it count as the universe? is more the question. What are the physics of areas? We're getting very theoretical now. We're not studying that shit.
Expansion of the universe is a very weird thing because, yeah, the universe isn't expanding into something as if a balloon expands into something. It's more like the surface, like it's you can kind of look at it as if it's a balloon. Like the surface of the balloon is a good way of looking at it, but it's not actually expanding into something because the universe is. It's expanding into itself, but it's weird.
Yeah.
There's some good videos on it, and it always boggles the mind. Yeah. What Champ said.
Yeah. And local scales are big. Don't mean like your neighbor. We we mean like several galaxies away. Yeah. Like it's not even
Yeah.
Like expansion of the universe isn't even the dominating factor between galaxies. Gravity is still dominant there. Hence why Andromeda is going to hit us.
No, don't hit us, please.
So
Okay.
you're looking at beyond groups of galaxies level, like probably even beyond groups of galaxies. I'm not quite sure what the distance is. Maybe we'll work it out at a later date. But it's numbers of
That's true, champ.
megaparsecs.
That's true.
Numbers of megaparsecs, and
Be a
it's
real
1
party
megaparsec
here.
between galaxies. So there you go.
Okay. Well,
Good old milk drometer.
we've looked at these equations enough now. What do you do with them?
I don't know. Oh, you do what I just said. You use them to measure.
I thought that
actually,
was like leading into a next question or something. Whatever you.
no. There's no question on using these yet. Essentially, what it is for tracking things through the universe as it expands, because you need a coordinate system to do that.
You've got time. You've got a difference in time, a difference in its distance from something else, and well, this is just its coordinates, and this is the time, its location in time.
Let me see if I can find the relevant drawing I did.
And let's see what happens over time.
Is it that? No, this is some positive curvature
again.
shit. Okay.
Fine.
I'll draw it. I'll draw it separately anyway again.
Fair enough.
No, it went badly. Stream quality. Stream is blurry or pixelated. There you go. I've told them.
Good. That'll show them.
That will show them. They're sure to fix it now. Right, there we go. That's back. Oh, I shouldn't have done it like that. Never mind. Right, so essentially, let's say you have a thing. Here you go. Wow, this is a plane. And it's got shit on it. Let's say we've got 3 points like that. Then as time goes by and the universe expands, we get the same shit, only bigger. And now the distances between them have grown. However, relative to each other, these are the worst. I drew them differently. I see. That's why the lines are bad. Hang on. Let's rearrange those dots. We got one here-ish, one here-ish, and one here-ish. They should probably spread out more than that. But essentially, pretend I'm drawing straight lines. Oh, for fuck's sake, that's terrible. I'm just not even going to draw lines between them, because Jesus. But using this, you would track how those objects would move in an expanding universe while keeping them relative to each other. Assuming no other motion, but you could incorporate that into the equations if you wanted. Oh, I see. You're smart, so you're just copying and pasting and making it bigger.
Yeah, that was my plan, but I instead just moved it.
Nice.
I need to copy and then paste it first. Then move it here. So like that, and then.
Good work.
Yeah. And we'll draw some very good straight lines. Here, here, and here. What were you actually trying to show? That the like
that they remain relative to each other.
Yeah.
Yeah. So their distances on the expanded plane.
This distance is
when scaled to the plane the same. That's scale factor shit. Here's a question that I want to know the answer to, right? If I this is nothing to do with an assignment, I promise. If I, right, were looking at a galaxy within the universe, and let's say a question said that the scale factor of the universe is increased by a factor of 10. Or rather, the scale length of the universe is increased by a factor of 10. Would you assume that the galaxy is also increased by a factor of 10?
I don't know. Say that again?
So let's say, right, a question has asked, so in a previous question, let's say, maybe you have measured how much of the volume of the universe is taken up by a galaxy. And then
Okay.
let's say that the next question says, or rather by all galaxies. And then let's also say that the scale factor of the universe is increased by, the scale length of the universe is increased by a factor of 10. How would the how would this percentage change? Would you assume in that question that the galaxies are also increasing by a scale length of 10?
Well, no. I'm assuming the galaxies themselves are staying the same scale, right? It's just there's more universe, so there's less. So the galaxies take up less of the universe, right?
Because that would then be taken by volume, and the answer would be, I mean, the prospective answer would be
So the
10 to the power
hypothetical
3.
answer in this non-existent question.
Yeah, the hypothetical answer to that non-existent question would be 10 cubed because it's a volume.
Sure. Hello, Jay. What you're seeing right now is this is a part of space-time in a certain curve and whatever, and it, due to the expansion of space-time, these 3 points on here are expanded, and these distances are larger, but the what's the word? The ratio is still the
Relative.
same. Yeah, relative to
Positions.
yeah.
Also, the angles between them are the same. That's the other important factor of that.
Yeah, that's true.
Okay, I'm just
But,
going to quickly make an adjustment to something I typed earlier.
Yeah, it's got nothing to do with
No.
anything that
No,
we
of
talked
course
about,
not.
though, right?
Of course not. I can't believe Champ's ratioing us.
Ratio.
Let's see. Let me just
Expansion plus ratio.
get rid of that sentence because that's clearly not the case. So, radius and thickness of the galaxy would not change. So, blah, 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 blah. So I can get rid of that sentence. And, okay. So, a scale length change in scale factor increase, I should say. Increase in all directions by a factor of 10 would result in a volume increase for the universe of 10 cubed, which is something I'd already typed in this answer.
What do you mean? What answer? There's no answer.
I mean, yeah, the hypothetical answer. No, I mentioned a hypothetical question before this. That's all I meant.
I see. Yeah. So okay. I see.
And so, yeah. Assuming no increase in the amount of galaxies, the average distance between them would also increase by a factor of 10 cubed. Copy paste, because typing out 10 cubed is a pain. And that's pretty linear. So that would increase, but yeah, so the percentage change would decrease, would change would be to the factor 10 to the minus 3. Brilliant, because that's the percentage of the universe taken up by galaxies decreasing by a factor of 3. Factor of 10 to 3, should say. Lovely. I'm sure that I think the way I worded that would have meant I'd have been fine anyway. I mean, hypothetically, because I made it pretty clear that I was answering it under the assumption that the galaxies were also changing and noted all of the sums I was doing. I even said how it was changing. Anyway, that's fine. I mean, what?
What? You could just have both.
True. I thought about that. I thought covering all my bases would be somewhat strange. Because when I think scale factor, I think like, oh, actually, no, that drawing is the example, isn't it? The galaxies themselves haven't changed. It's just all the distance between them.
Yeah. Also, just like if literally everything becomes larger, then nothing has changed.
Yeah, exactly. Which I thought was a strange answer. Well, but the hypothetical question has what if anything would change. So 0 was a potentially valid answer. But anyway, case closed. So here's another interesting hypothetical.
Okay.
What aspects of the FLDW equation do you think determine curvature?
Okay, well, let's bring them back up. That's the wrong one. This one. These ones. What aspect determine curvature?
Let me just check. Or even even homogeneity and isotropy. An interesting question, isn't it?
I don't know how they'd represent homogeneity. Like, thinking of like the curvature and isotropy, which is it's all about angles, right? Like, the first thing I think of is the d omega, because, well, that's the one that's got to do with angles.
That's the one that highlights curvature.
Yeah.
That was, I think, pointed out in part of the conversation that we were having about it. So,
well, I wasn't listening, but it's just this one is the one that has to do. Oh,
fine.
Well, this is the one that has to do with angles, right?
Yeah.
So it makes sense. The one homogeneity, I guess, the only other one is like whatever this is. I don't know what this s squared of t is. It's just some like locational function of time. But maybe actually
it's a function of time. That's all it is.
It's just a function of time. Well, then it probably is the dr, right? That's the only one that actually has about distances. For the homogeneity, right? Because all the rest is about time and how time changes.
Yeah, well,
and that one is about how location changes.
Yeah, so the first part of the equations is
an
a constant.
SKR here probably.
Yeah.
Just like the two answers are in this part. Because
Yeah. Well, yeah, because the first one's constant all the time.
Maybe I don't know what that means, champ. Is that true? Is S the space-time interval?
I don't see. Not in this. I don't think. It just said like all the note says here is that it's a function of time. It is also replaceable by a of t, which is different. That might be the space-time interval, and the s of t is something different. They can both be used kind of interchangeably, but they do represent different things.
Interesting.
So pass on that one. So, as we've seen, that first equation we know pretty well that Sorry, I'm trying to think about isometry and isotropy even, and homogeneity.
I kept calling it
Because
isometry as well last time.
yeah, whatever. Same thing in it. No, it's not.
It's not. It's not. It's very different.
Because homogeneity is that it's the same everywhere, and isotropy is that it looks the same in every direction.
Yeah, so it's
So
rotationally the same.
yeah. So to determine, sorry, just let me determine what this hypothetical actually wants me to do.
The space-time interval is the length of the path through space-time that the geodesic has. Space
kind of
what
vague.
time interval between events. Yeah.
Oh, of course. Okay.
Okay.
Sure, whatever. That's fine. Hmm.
Also, something that we
Interesting.
maybe didn't really point out, and I'll talk about later when well, not today, but another time when we get to derivatives and stuff, is that these d's, all these values with a d, stand for a change in something. Is basically what it means, and that might help understand a bit more what this is. Like because I can understand if you look at this. This is a lot of equation,
Hmm.
which can be very confusing and not really that interesting. But yeah, so this is just an equation that talks about differences in like changing in time of change or changing in space. T is time, R is like your location basically. Well, it's like the well, I don't know what this R specifically is, but if it is the same R as the ones we had earlier, it's like length from a certain point, basically. The distance to a certain point, and then these omega is the angles. So it's the
Yeah.
location as if as we were talking about earlier, like in here, like these ones. Um. See, I literally what I just said. We're talking about space time, George. This might be more fun to look at.
There you go. It's a nice drawing.
Are you doing anything? What?
No, I figure I shouldn't do my assignment right now, so I'm not.
Okay. Is there anything else you want to talk about that is related to this?
I don't think so.
Is there anything else you want to talk about? And
Oh yeah,
does it involve limits?
potentially. We are moving on to galactic astrophysics, which is in a lot of need of this change of format because
It's
because
just
the
a lot of
reason
things.
yes, because the reason I didn't know the answer to any of the questions last week is because we hadn't covered any of the questions last week. Turns out that is those
That will
questions with
explain
the
it.
syllabus for the semester, not the syllabus for the first week. So when I
That
didn't
makes sense why
understand any
there
of
was
it,
like 500,000 questions.
that also does make sense. I was wondering how he expected us to do that in 2 hours. Anyway,
Let's see. Well,
that's right. We're going into gastrophysics, and the first part of that is fluids.
gastrophysics.
I am at the first part of that is actually physics. Isn't that lovely? Right, let me just
Is
find
it
where the
actually
fuck we are.
what? Is it gas as in like it's a gas?
Astrophysics. What are you talking about? We're not
What did
talking
you
about
say?
gastrophysics.
What? That's what you said.
No, that's what George said. Do you not read your chat as messages?
No, I didn't read that. I thought you were. You said that like in your sentence. I didn't realize you were talking about.
I'm sorry, I'm so sarcastic.
I was first listening to you, and then I was gonna read chat.
There is no change in my voice from normal to sarcasm, so it is
Exactly.
quite difficult.
That was just astrophysics. Yeah,
Let's
let's
make
make
up
up gastro.
gastrophysics.
Is gastrophysics not just like food physics?
I guess so. I may imagine it's how
See,
explosive your
Julie was also
bowels are.
confused. Ooh. Yeah, that could be like rocket science, but for your bowels.
Yeah.
What? How much fuel do you need to get to achieve liftoff?
Why did
And by
all of you
fuel, I
believe
mean.
in gastrophysics? I don't believe
I didn't
this.
believe in gastrophysics, but you just said it like as if you were talking. I was like, what? Did I hear that correctly? And that's why I was confused when I asked it. Whatever.
This is a
Whatever.
nightmare. Anyway, we spoke about last week some of the structures of galaxies, the main parts of them, the galactic disk, maybe the stellar bulge because that's part of a galaxy, and fluids is next. So fluids is kind of tough. Essentially, there's two different ways of looking at the fluids. One of which is called, well, the way based on this fella's name, which is Lagrangian.
Well, its name's Lagrange.
Whatever. There's a Lagrangian looking way of looking at fluids, and there's the second way, which is by
You
a
know
man called
your screen's
Euler.
actually looking at mine still.
Mine's still on it though, right? Yeah.
Yeah, but really small. I can't read that
And in
shit.
really bad quality too.
Your mum believes in gastrophysics too. It's
Yeah.
good to know.
And the other is by Eulerian. I'm gonna reset this quality.
Euler.
Whatever. Not my fault. He's French.
We spoke about this last time. We've got.
Oh, yeah, we did, didn't we?
Lagrange and Euler.
Discord's gone.
Two mathematicians who've done everything.
Yeah. Oh, fuck. Right. Discord's gone again, and I can't restart it. So, we're going to look at your screen again.
Incredible.
Despite having nothing on mine. There you go. You get the picture of the default profile picture of my tablet. Because apparently... Oh, yeah, I clicked on it. But I can't stop the stream on my tablet, but I have stopped it, actually. So those were just two different ways of looking at fluids. Lagrangian looks at it in terms of a time change on the fluid, and Euler looks at it as a space change on the fluid. So what changes in a given space for a fluid versus what changes for the fluid as a whole over time. That's it. That's it. Then there's a whole bunch of maths for it.
Incredible. Well, shall we talk about limits then?
Yeah, we should.
Good.
I'm trying to think, is there anything else in this that would be useful to talk about?
Or that you could talk about, that you know enough about to talk about?
No.
Or that can be like something visible, you know?
Honestly, it's just all equations.
Well, great. Shall we talk about limits and try to... This is what I like to call calculus with redux. We need a better name for this part. Simple calc. So, calculus. What is calculus? I don't know. Who cares? That's not important. We're talking about limits today. Limits. Boom. Simple calculus. Limits is a thing that is super useful and super needed in physics and in a lot of math. Exactly wise. In a lot of maths, but is actually, which is very basic in a way, but it's mathematically it's a bit hard to describe limits, but it's so it's so intuitive. They're so simple to understand. Everyone can understand limits, and I hope that everyone will understand limits. So for example, first of all, what is a limit? Let's say we're looking at a function, right? This is just like a normal function in 2D space. You've got x and y coordinates, and this function goes like this. But there's a problem with this function because over here there's a little problem. The function's not defined in this one point, right? Let's say the point, I don't know, A. That's a problem. It's a problem. The function is not defined there. So we're like, okay, it's not defined there, so just whatever however we would write this function mathematically doesn't, if you would fill in the point A, we'd get a problem. And that's annoying. What are we gonna do about this? We don't want to have this problem. So what if we just like have a look at this point and we just get like real close to it? What if we just get real close to it, just right next to it? And instead of actually going onto the point, we approach it and we go, oh, at this point we have this value. Okay, that's, that's probably what could be there if we would imagine a point in this place. If we were to replace it with a function that is continuous, but we've not defined continuity yet, but whatever. We'd get that, and then we get a bit closer, and then, oh, that gets us a bit closer to this point, which we're going to call B over here, which is the exact point that this would be, right? And we get a bit closer, and if we just keep going, we get closer and closer and closer to this point until we're so close that we're just not on it, right? And if we keep getting closer and closer, we would get to the point, and then until we'd get past it. And then we're here. And we can do the exact same here. We can approach it from this direction as well. This point, we can be like, oh, this, until we get closer and closer to this value. And then you notice that, well, it's actually because of the way I drew it. It's around this point, but whatever. A better example would have been just a straight line, but whatever. We're going with this. So we get closer and closer to it, and that is called the limit, which intuitively is very simple, right? We just write it down like this. The limit of this function, so let's call this function f of x, which is a very standard notation of a function, without having to write anything. The limit of this function, f of x, as we approach x, as we approach on the x axis, we approach it, we approach a, that limit will become b, right? We get closer and closer and closer until we get to b, and that makes a lot of sense. This is very intuitive, very easy to see, right? Let's just say we have like this thing, and we have this in here. Okay, whatever. We're going here. We have some function here. Let's say this is just x equals y. The simplest function you can have, right? It plots 1 onto 2. Sorry, onto 2. What am I saying? Onto 1, 2 onto 2, etc. But we're saying this is that function except for, so this is defined for every x except for 2, right? For every other, it's just not defined in x is 2. So, but we can have a look at this and we can take the limit. So if we take the limit of this function, let's call it g of x. If we were going to take the limit of it, of x approaching 2. Now, normally you can like you start limits by having two limits, a left limit and a right limit, because you can approach it from two directions, right? And that there's a difference. But for this, it's okay because it will both go to the same place. And we see if we approach this, this is really easy. This is obviously gonna be just the limit of is 2 as we approach it again, because x is y. It's just not, like, as we get closer and closer here, if we get to, like, let's say we get to 1.99, if we fill in 1.99, which is defined for a function, we get the result. For y, we get 1.99. If we get really close and we come here and we say 2.001, we would get 2.001. And we get closer and closer. And as we get closer and closer into the limit, we get this point and we can find the limit. You can also just find the limit of a point even if the function is defined there. So, for example, if we take this same thing, hospitaling. You're horrible. Fucking l'hôpital. Why is there an E in there?
I've never heard the term hospitalizing to do with limits before. What does that mean?
Well, Champ is referring to the rule of l'hôpital.
What?
Which is
it's a comment. Oh, I didn't realize.
Yeah. I love going to the Slay Hospital. Yeah, basically, Champ is saying Slay and l'hôpital. So yeah, if we could just find the limit as well here of this point, which is defined, and it's exactly the same. We get closer and closer to it, and then we can see that, oh, the point that is in between there is 1. It's very easy. So true, Niv. So true. Now, that's all cool and all. Now, the way limits are defined mathematically is they use epsilon delta definitions is what they call it. And let's say you have this point. Let's say we have this whatever function it is, and this is the point we're trying to find the limit to. You have this point C down here, and then L is just the limit. So let's say the limit, whatever, of the function of x going to C is L. We just define it as L, right? The thing is, what they say is, if you give me any epsilon, so any small number, I can give you another number so that a delta, so that it's the limit will always be within a certain interval. So let's say you want to say, let's say this distance. You give me an epsilon that is this distance, for example, which is this point, which is L plus epsilon, and this point, which is L minus epsilon. And then I can give you a different one. I can then say, well, if I take a delta so that it's between this value and this value. Like, for this one, it's just like reusing these functions. Like, it's really easy. Sometimes it's a bit annoying. And we just take any delta. We can take any point in here. So we can just say, like, boom, here and here. These 2 points. And then we have C minus delta and C plus delta. And then we found that the limit will be within these, like, the limit of C will be within these values. That's the mathematical definition. But the basic idea is you give me a range that you want, that your limit is in, and I will give you a set of values that will have the limit in it. Which is, it's a bit confusing. Like I said, it's hard to mathematically explain. It's hard to mathematically define it. It's confusing, but the idea of a limit is very simple. It's just you're approaching a point, so you're approaching a point closer and closer and closer, and you find what it would be, and limits are a way to have a function that isn't, like, for example, if a function isn't defined in a certain spot, you can find the limit there, and then you could have a definition of the point. You can add it to your function, which is something like, for example, let's say we're trying to find the limit of x going to let's have a think first. Let's say it's like x squared plus x minus 1. Is that correct? Is that a good one? Sure. And then we'd be going to 2. Let's say we're going to 2. And then we have here x minus 2. I think that's correct, yeah. So if a normal way, like how you'd find a limit, is just you fill it in, right? You fill it in, but the problem is, if you replace 2 with, if you replace x with 2 here in the denominator, is that what it's called?
Yep.
The denominator, you'd get 0. But also here in the other one, what's the other one called?
Numerator.
No. You've got the numerator and the
Denominator.
Oh, I see. Oh, sorry. So this is the denominator and this is the numerator.
Oh, I see. That must be the delay I was having. It looked like you were pointing at the other one. Never mind.
Okay. So yeah. Then you get the top one, which is the denominator.
Numerator.
Is it? Wait.
Top is numerator, bottom is denominator.
That's really fucking confusing because in Dutch, the denominator is called the noemer.
Oh.
So that so in my brain that's like numerator, but it's denomer. It's name because it's numer. Numer is like the namer, I guess. And then the other part is the teller, which is way easier. Anyway, this one would also be 0. If I'm correct, right? Because you've got 2 squared, just 4. It's not true. I did it wrong. If we do it the other way around, it will be. Will it be?
What are you doing?
It should be 0 in the numerator as well.
When x is 2. Right, everyone, do some maths. That would be x squared minus x minus 2. Which isn't any help. Because you would cancel some of that out, I imagine.
Wait, give me 2 seconds. X squared gives, so we get 4 minus 2. Doesn't work. Why am I stupid?
I'm not entirely sure what's happened.
Oh no, it is. No, I'm stupid. It's. This one isn't 1, it's 6. I was thinking of the wrong.
Okay, so it's x squared plus x minus 6.
Yes. That was it. That should be 0, right?
Yeah.
Yeah, there you go. Okay. I was just stupid. There you go. So yeah, that becomes 0. If we would fill in the limit. That becomes 0 divided by 0, which you can't divide by 0. So this function, if you would plot it however it look at 2, you wouldn't be able to plot it, right? Which is a problem. But then we can find the limit. We can figure it out. We can change this a bit. Like, for example, if we factorize this polynomial wise, we'll get a kick out of that one. We get x minus 2 and x plus 3, I think. yes. Which is a bit easier if you look at it like that. Yeah, long-term fans really love the polynomials. That's true. That's true. Which then, if you've done any math, you'll probably, your math sensors will probably be going off that you can cross these off. And then this just becomes the limit of x going to 2, x going to 2 of x plus 3, which is way easier with the clause that this function is not defined, like x plus 3 is not defined, so it wouldn't look like this. In fact, it would look like a straight line. Let's draw it. This first function here would look like x plus 3, so it'd look like something like that. And then it's not defined up here. Boom. But if we can still find the limit to it. This is just like the thing I drew up here earlier. One of these. Yeah, this one down here. It's just like this. We can still find the limit here. And if we take the limit, the easiest way to do it is just fill it in x, and boom, we find that the limit is 5. So this would be 5. So if you want to make this into a continuous function, which continuity is defined off of limits. In fact, it's defined off of something is a continuous function. I think is the definition is if the limit is the same as the function in everywhere. I think, and you can take the limit everywhere. Is I think the definition of a continuous function. Because something else interesting with limits is, let's say you have this function. Whoop. And in this spot, it's not here, but in fact, down here. For some reason, this function plots 2, not onto where up here you'd follow the curve, but it plots it down here to -1, for example. That's all cool, but if we take the limit of this function, of x going to 2, we find that, well, when we get closer and closer, if we approach it from this side, we get closer and closer and closer and closer and closer, and we get around here. And from this side, we get closer and closer and closer and closer and closer, and we get here. So at the end of the day, if we find the limit, it's going to be over here, and we're going to get like 2, whatever. Which is interesting, because this function is defined over the entire x-axis, so you can plug in any value you want, and you'd get an answer, but it's not continuous because the limit in 2 is not the same as the value of the function in 2. Which makes it discontinuous. Which is an interesting thing, because continuity is something that is needed for a lot of things in like higher maths, higher calculus and stuff. A lot of things need, like, this is true if the function is continuous. This is true if whatever, like the function needs to be continuous and the limit needs to exist and that kind of stuff. And then there's some fun stuff you can do with limits. There's some interesting stuff, not like less graphical. Like you can just, there's some interesting things. Like limits are very simple to do math with, because basically if you have like fx plus gx, for example, and you'd want to take the limit of that to whatever, it doesn't matter. That'd be the same as if you were taking the limit of fx plus the limit of gx. which is very easy. So if you've got something confusing, you can slam them together, and then you get a limit. Suddenly the limit exists, even if the limit didn't exist beforehand. Or this works as well for multiplication, for subtraction, for division. Some interesting stuff, like for example, if you take the limit of theta going to 0 of sine theta over theta, well, you get 0 over 0, because the sine function, which you can plot on a circle, or you can look at the value on a circle, if you plug in 0, the sine function starts at 0. So go whoop, whatever, like that, right? You just get 0. And well, yeah, in 0, theta is just 0. So you get 0 over 0, which is annoying. So how would you figure out what this is, right? Well, so you can just very simply move it in. Well, actually, it's not very simply. This is a bit annoying. But yeah, the way you figure it out is by moving the limit up here and moving the limit down there, which we kind of intuitively did up here as well, over here. That's how that's how we figured out this was 0 over 0. It's just intuitively you take the limit of this top polynomial, you take the limit of this down here, and both are 0. So like I said, limits, very intuitive stuff. A bit more confusing when you start writing it down sometimes, but it's very, very doable. But yeah, another interesting thing is, we'll come back to this. If you have a certain function like that, and another certain function like that, and they approach the same value at a certain point, I should have drawn them in color. You have this function. Okay, we're gonna just redo that. You have this, and then you get the second one, and they do that. You have this function f of x. This is getting fan servicey now. I'm sorry, boys. I'd like to apologize. And let's call this one h of x. And then if let's say we have a function that we know is smaller than h of x in every point, and larger than f of x in every point, we call it g of x. So we have f of x is smaller than g of x is smaller than h of x. We can see that the limits of these, and let's say specifically we have a point over here, whatever, that we know the limit of h and we know the limit of f in that point, well then we know that the limit of g is also going to be the same, which is called, what's it called? The squeeze theorem, I think is what this is called, which is a fun name because it's such a stupid name.
Sounds great.
Yeah, it's the squeeze theorem, which just means you're squeezing the middle one in between the other two, and it literally has no other way to go. And that's how you can find this one, I believe. Because the limit of yeah, the smallest the sine could ever be is -1. So let's say some other function, whatever, we know that the limit, wait, am I doing this right? Whatever. Who cares? Basically, the sine of this other function that we have is going to be smaller. It's the smallest that sine will ever be. Okay, sorry. My brain is just, I know what I'm going to say now. So, the smallest the sine will ever be is -1. The largest it's ever going to be is 1. So, we know that this limit is going to be between 1 over theta negative 1 over theta even. We have this limit. Theta going to 0. Sine theta over theta. And then I think I'm confusing two together, but whatever. Because I think for this one do you actually need L'Hopital? I think you might do. I swear there's another way. What am I actually thinking of? What are you doing?
Sorry, I had to drag your window down to get the bottom of it in, but then I realized why I didn't do that in the first place is because the red boxes go up that high.
I see. Yeah, my boxes are covering it as well. I know. It's confusing. I'm thinking I don't know why I'm confusing these two. Because this is something else I'm doing. And I'm confused. I've confused myself. This is great. This is great math.
Yep.
Because okay. I'm not in my thing. Here we go. This is unrelated. There's a way to do it by upside downing it and doing cosine while squaring it. Maybe that's what I was thinking. Maybe it is squared. Cosine squared minus 1, which is the same as sine. And then okay. You know what? No one cares. Maybe they do. I'm looking up. Sine sine x over x. I was literally looking at this yesterday and I've confused myself.
Nice. I've drawn the most simple case of limits, which is y equals 1 over x. Which is
Well, yeah, that's an interesting one that I was going to go to later, which is limits of infinity. And limits going to infinity. This is way too long. I need a shorter one to look at. Fuck off. This is something weird. Okay, I don't know what I was looking at yesterday. I was looking at something else, and I've confused myself. I need help.
well, you get none from me.
This is all good. That's how to do the tan. See, I knew it was a squeeze theorem. Okay, I'm looking back at squeeze theorem. I think it is just a graphical one, but I'm just doing the wrong ones. The limit of, here we go. Okay, so instead of what the fuck I was saying, isn't this one solved with identities? Well, this is just an identity, isn't it? Instead of what the fuck I was saying is the fact that there's multiple ways to solve it. You can do it with L'Hopital's, but what I'm actually doing is if you see that the cosine of x, okay, not x, we're using theta, is smaller than or equal to this, what we had, And that is always, it's always going to be smaller or equal to 1. I was right there. I knew it was 1, but I got the other side wrong. And through that, if we then both of here, yeah, this is it. So then, because of the squeeze theorem, like I said here, if we take the limit of f and the limit of h, and they're the same, which, well, the limit of 1 is just 1. But then if we take the limit over on this side, yeah, exactly. If you do L'Hopital, you'd well, you take derivative of this and you take derivative of this, which is 1, and then derivative of that is cosine. Yeah, it's cosine, and then the cosine of 0 is 1. Which is exactly what Champ said. But L'Hopital is not, we can't use L'Hopital because we're talking about limits. And without limits, you can't define derivatives. So how are you gonna do derivatives if you don't know what limits are yet? So the limit of theta approaching 0 in this one, the cosine is the same as the function. Sorry, what am I saying? Cosine is the same as the sine, but shifted over one, so it'd be like this. I drew that terrible, but no, that's actually whatever. It'd be like that. This one's just drawn badly. The first one, whatever. And basically it's 1. So this is 1. So if this limit over here is both smaller or equal to 1 and larger or equal to 1, sorry, this is smaller, this is larger, well then it has to be 1. So boom, that's how you do it. And that's the squeeze theorem. And I just had the wrong functions to squeeze in earlier because I was stupid. That's very cool for you, Champ, but that's wrong. It's wrong. And then, like Wheat says, let's look at what Wheat has done. I need to look at it again. What are you doing?
A proof of the thing you were doing. I thought I might finish before you do.
Let's see. What, the squeeze theorem? Or just
this is a different proof by the
one?
looks of it.
Oh, a proof that the limit of sine x over x is 1.
Hmm.
Yeah, I think this is the one I remember learning, because I remember there being a tangent. That is one I learned. I don't know.
Because it ends at the roughly same point.
Well, yeah, at the end of the day, you're going to use the squeeze theorem for this as well. Or L'Hopital. Yeah. There's like the two options, really. Which, yeah. If you want to see what Wheat is doing, go over to Wheat's channel. You can see it very small at the bottom.
Fuck's sake. Whatever, it's fine. You're doing the more important stuff anyway.
Yeah, but I wanna see what you're doing. Actually, you know what? Fuck it. It's now also on the main screen. So yeah, that side becomes 1. This side becomes 1 over cosine, which then you turn around. Well, you invert everything, right? At this point, it's like, at this point on, you can kind of do it, right? You don't need to think. What? Why is that sine at the bottom? Sure, that's cosine, right?
Hang on. Give me a sec.
Yeah.
I skipped a bit. I need to zoom in on this because it's actually more than I thought, so.
Is it? Are you sure it's not the sine at the top still at the other side?
Yeah, it is, sorry.
Yeah. I skipped that step.
Okay. What a lovely, anyway, there we go. Yeah, that's what's going to happen.
And yeah, and then those two signs cancel out, and so you have 1 over cosine, and then you turn everything you invert everything, right? Because you need sine x over
Yeah.
x and not x over sine x. And then inverting it means the what's it called?
The less than switch.
Yeah, the less than switch around. So you get 1 is larger than or equal to x over, no, the other way around, sine x over x.
Yep, wrong line.
I want to know the start of this one though, because you didn't actually show it. But yeah, like from here on, you get x, and then the other side is cosine x over, and then if you take the limits of everything, the limit of cosine x, it's exactly what I just did. Like at this point, we're at what I had.
Yeah.
This is what I. Wait, what's happened to my? I've lost it.
Nice.
Wait, what happened to my? Huh? What? Did I not? Did I delete it?
Undo.
Oh no, it's on this one. Here it is. Here it is. I did it, and I was just on the wrong scene, on the wrong layer. So yeah. So which is then this, and then if you take the limits of cosine, you get 1, and the other side is already 1. So you get boom, sine theta over theta, or sine x over x, which is exactly the same as this one. Can you go? Oh, it's died again.
Oh.
I want to see what the start of it is. So you say that x over 2 is larger than sine x over 2 is smaller than tan x over 2.
Yeah.
Okay. Which
So
math course is it? We're talking about limits right now.
So that starts from this, which is very badly come up on screen, unfortunately, which was to be expected.
To be expected, yeah.
By someone called Ali.
Yeah. So what you've got is a unit circle, and then from there on, wait, let's just draw that. So what is that? You've got a circle. Oh god, I've got fucking. No, that's even worse. We're gonna keep it on. We've got a circle, unit circle, whatever. This is gonna be a terrible sketch. We've got this is the sine, this distance, and then the tangent is this distance. And is that true? Yeah, and this is the cosine. And that's the tangent. So then you have the fact that x, which is well, x is the same as cosine in this case, right? No, that's not true. That's not true at all. That's not true at all. X is the angle. Which the angle is, if it's in radians, is on a unit circle is the same as this distance. This curved distance, right? This distance. And then from there on, you know that this curved distance, well, yeah, this curved distance is going to be, it's going to be, well, they're all divided by 2 for some reason. But that curve, the absolute value of it anyway, is going to be larger than the sine. And it's going to be smaller than the tangent, which is this part. I'll do it in color. So this, fuck's sake. This length is the tangent, and this length is the sine. That's just how they're defined. It's just the definition of them. And then from there on out, well, it's the same as if they were divided by 2 or whatever. Obviously, that's the same. And then What else do? You just divide it by x, I guess? Or what do you do? No, you do 1 over, I guess, right? Well, tangent, you split it in sine and cos. That makes sense. And then you divide. Okay, it's just... Why does it start by divide by 2? I don't get that part. Because surely just this length is smaller than this. It's larger than this, and this length than that.
Good question. I imagine that comes up earlier in the thing he's written here.
Yeah, whatever. Even without these. This is a great... We don't care about specifics here, okay? We don't care about specifics here. So if we know this, well, we know that the definition of tangent is sine over cosine. So we can replace that with sine of x over cosine x. Now we get to what we had earlier. And if we divide everything by sine, this side becomes... I'm not writing it all down again because we did this already. This just, like, if we divide it by sine, we get 1. Here we get x over sine. And then this leaves. SOHCAHTOA. That's true, champ.
The other 2's came in because at some point earlier in this, area was involved.
I see. But I think, like, it's hard to just say that this is true, I guess, without looking at areas, but whatever. It's too big for its breeches. What are you saying? But yeah, and then we divide by this, and then we just do that to everything, and you do 1 over, which flips this one around, flips that one around, so that is cosine of x, and the cosine of x evaluated at 0 is that's not correct. Why am I stupid? Are we evaluating us at 0? Have I stupided myself?
I don't know.
The cosine's 1. How's the cosine 1? Am I stupid? Oh yeah, of course. I'm sorry. I am being stupid. I'm just being stupid. Don't worry about me. Don't worry about me. I'm just literally stupid. The cosine evaluated 0, which is this angle, is this length over here, and that is 1. So we get 1 here, we get 1 here, and then why am I using this horrid color? 1 here, 1 here. These have switched because we've done 1 over. And you can see that, for example, if you see 1 over 2 is larger than 1 over 3, but if you flip them around, you have 2 is smaller than 3. Boom. You can see it like that, and it's exactly the same, but with this. And now we have here sine x over x. And these are absolute values, which I think is important, but I think it just works anyway. I'm not entirely sure. So yeah, this limit, this is important that it says limit in there, whatever. Boom. That's just what we did. It's the same proof. But now we've looked at limits a bit. We've looked at how they go into infinite. Well, we've not looked at how they go infinite. That's the next thing, is what I was saying. We've looked at the squeeze theorem, which is very, very fun. But now, something very fun and very intuitive, I feel, with limits. Like, it's a lot of wishy-washy, you just kind of vibe with it if you do math with infinity limits. But it makes just a lot of sense. So let's say you've got this, and you've got 1 over x, that's what you wrote earlier. The function is that one. Well, it looks like this. And here in the middle, at 0, That's the worst line ever. It climbs so steeply, and it doesn't stop anywhere, and it doesn't intersect the y-axis ever. It just keeps climbing forever. So we call that an asymptote, which if you look at it at this like numerically, if you would take the limit of this function of x going to 0, well, you try to fill in 0 here, and then you'd get 1 over 0, which, well, you can't divide by 0. So if you get a number that isn't 0 over 0, that means in that point you've got an asymptote in your function, which means it goes up or it goes down in a direction, and you're fucked, basically. It goes to infinity and beyond.
Mm-hmm.
In this case, it's different which side we approach it. If you approach it from the left side, you get negative infinity at this side. Approach from the right side, you get positive infinity. So the limits on the left side and the right side aren't the same, which means the limit in general doesn't exist. Now we have something very similar over here. If we keep going along the x-axis, we keep going infinitely far, this line gets closer and closer and closer and closer and closer to 0 over here. Closer and closer, which we have a horizontal asymptote. Which is a bit freaky, because the way we'd write that is we take the limit of x going to positive infinity of 1 over x. Which means we'd fill in 1 over infinity, which is weird. Like, what the fuck is 1 over infinity? But that's just something you learn. 1 divided by infinity, any number divided by infinity is 0. So you get 0. Boom. That limit keeps going to 0, and it does it in both directions as well. If you go to negative infinity, you also get 0, which isn't always the case. Sometimes you have an asymptote there and an asymptote there, which is interesting. So it approaches that real close, and it never quite reaches 0, but in infinity it would reach 0, is what that means. Which is it's a bit hard to define this in ways of where is it? Epsilon delta? Where did I do epsilon delta? Where the fuck did I define? Okay, whatever. Here it is, actually. It was here. It's hard to find this in ways of epsilon delta because you can't just give like infinity plus delta or infinity minus delta, because, well, it's still infinity. It's a bit harder mathematically to define these. But we don't care about that. It's not that important. Like, what I really want from this, like the calculus things that I'm gonna be explaining in this and other weeks, is that you kind of understand the concepts that we're working with, and that they will show up in Wheat stuff a lot. Like, limits is kind of basic, and they don't show up themselves, but they're needed for things like derivatives or things like integrals and stuff like that. You need limits because they're defined in terms of limits. So it's a basic for the next week. We'll have a look at derivatives, I guess. But yeah, this is quite interesting. And then the last part. There was like one more part, I guess, but it's not that interesting. No, say what you were gonna say.
I was just agreeing. Yeah.
Oh, I see. Yeah. Okay. It sounded like you were gonna say something interesting.
No,
but no,
I was just saying.
Never mind.
Yeah.
But yeah, limits to infinity are quite interesting, especially if you're doing it with like confusing functions, because these are basic functions. But let's say you have like x power 5, you do like x cubed minus 6x, and then that's like divided by say you've got like 4 and then here like 6. Minus 6 x cubed plus 3x, for example. Plus 2. Let's say we're taking the limit here of x going to infinity. First of all, how the fuck are you gonna do that, right? Because if you can visualize it, okay, you can look at what happens if it would go infinitely far. So if you would plot this function, you'd see this or whatever. You'd see, oh, this goes infinitely far. Well, it's kind of hard to see, but if you see it always keeps going up, you can kind of see it, but it's hard to... You can never know for sure if, like, maybe at x is 5 million, it suddenly turns and goes back down, you know? It's hard to see that. It won't. In this case, it won't. But, like, it's... You can't always, like, look at a function graphically and decide what its limit in infinity is going to be, right? So you need some ways to do it numerically, algebraically, even, is the word, I think. So, well, if we'd fill in infinity here, it gets confusing because we get infinity here. We get infinity plus infinity minus infinity. We get infinity minus infinity plus infinity. Like, what the fuck are we going to do with that, you know? What the fuck are we going to do with that? No, I was pausing the stream. That fucking cat. I love that cat. So that's confusing, but then we have to think about it, okay? So if we're approaching infinity, the closer we get, the larger these numbers are going to get. A number that is brought to the power of 5 is going to be way larger than any number that is power, like a lower power. So if we say, like, put in 500 here, like 500 to power 5 will be way larger than 500 squared. Will be way larger than 500 cubed, right? So you can kind of just ignore all other terms except the ones with the highest powers in them, in both the numerator and the denominator. So we can just kind of forget about all of this, which is incredible. I love that about limits to infinity. And so you see in here, and then you just have this. And when you look at this, we see, well, both of these are going to expand at exactly the same rate. They're going to become equally as big, equally as quickly, right? So we can just kind of forget about those as well. So we'll have one infinity divided by another infinity, and they're both expanding at the same rate. So if we get closer and closer, we'll have 4 times 5,000 to the power of 5 divided by 6 times 5,000 to the power of 5. So we could remove those, right? We could scratch those away from each other, and they'd cancel each other out. So weirdly, almost not intuitively, this limit is 4/6. So whatever this would look like, 4/6 being 2/3. Let's say this is 1. Whatever this would look like, in infinity, this would approach 2/3. And we'd have a horizontal asymptote over here at 2/3. Which is really nice. You can just kind of forget about everything else. Kind of forget about it. It's fine. It's easy.
Yeah. So say there was, that 4x to the 5 was 4x to the 6.
Yeah, so that's the...
Would in that case the limit then be just 4x to the 6?
Well, let's write that down. So we'd have 4x to the 6th over 6x to the 5th, and then there is other stuff, right?
Yeah.
We just ignore those. But so there's a difference. And in this one, if you're going to infinity, the numerator is gonna blow up compared to the denominator. Yeah, that's right. Okay.
Yep,
the numerator is gonna blow up compared to the denominator, right? So this is gonna be this is gonna get larger quicker than this one is. This one's gonna grow faster. A good way to visualize that is if you use x squared over x, because we can draw those real easy. X squared looks like that. x looks like that. So if we're going to infinity, this one is rapidly going higher and higher, closer to infinity, whereas this one is it's gonna get there. It's going to get to infinity as well, but it's gonna take a longer time. Like infinity is not a number, but whatever. So this one at a certain point, like even here, this one is way larger than this one. Like at the start, they're comparably. There's a it's important, but the further you go, this one's almost negligible compared to the other one. So that's why you can just forget these. You can just forget these. So what you do get is you get the limit of, well, you do this, so you get 4x over 6, and if you take the limit of this and you fill in infinity, well, this is just infinity, which means it's going to keep going up forever. So it doesn't stabilize at a certain point. It doesn't equalize out. It just keeps going up forever. And you can have a negative infinity as well. Maybe sometimes, like, if this was negative, it means that that one's going to go down there. Another option, let's say the denominator's larger. Let's say this one had the x to the power 6. What you get is a number, 4/6 in this case, or 4, divided by infinity, which, as we said earlier, becomes 0. So that, in that case, we would have some sort of function that approaches 0, just like this one. It approaches 0 in the limit, infinitely far away, that side. Yeah, which I think I love limits with infinities because it's just so, I feel like it's very intuitive, even if it isn't sometimes. Like, it's so simple. You just, well, forget everything. Well, especially with just polynomials. It gets a bit more involved when you've got things like any geometric function, like a sine or something in there. If you got like a square root, for example, you'd have to like get rid of the square root and stuff like that. It's a bit of a hassle, but at the end of the day, it's all just like Fingerspitzengefühl, as they say, to just kind of find the limit, which I like a lot. That's like, I don't know, I think that's very fun about limits. I think the only other part about limits. Thank you, champ. I just took my normal pen. I was gonna write with my normal pen. That was a great idea. Another part about limits I haven't really looked into too much, but it's needed for next time, is the intermediate value theorem. Which basically is, it's very useful when analyzing functions. It means that if you have a point, if you have a function and this is less about limits and it's more about continuity. So like I said earlier, a limit is a continuous function is defined by how every it's defined on the entire interval that you're going over, is every x in that has a function value, and the value, that evaluated value, is the same as the limit of the function as well in that point. So you get this and not that, because this one's not continuous and this one is. And then for, like, we can learn more about continuous functions. We learn something like the intermediate value theorem, which is very basic if you think about it, and it means that if you've got this point here and you've got let's just go this point here, this value here, we've got the value whatever 7. and we have the value 2, well then in a continuous function, in this interval, we're going to have a certain x that reaches, for example, 5. Because otherwise it wouldn't be continuous. So we need to find a point and it will lie in between them, the intermediate value, so that it will match that. And this then expands into I don't remember what it's called. Bolzano, that was it. The Bolzano's theory, which is basically the same, but if one of them's negative, if one of those two values is negative, so let's say we've got this. Yeah, there must be at least one point with that value in the... Yeah, there can be more. But it must reach it at least once. Otherwise, there's no way it can get there. It can reach it as many fucking times as it wants. It can reach it infinitely many times, but it will at least do it once. So this one is... If you have this one, let's say it's -1. You have this point, let's say it's +2. Well, then you know that 0... Well, which just makes sense because it's the same as the other, but more specifically intersecting the x-axis, 0. Because there must always be a point in this interval, that reaches this intermediate value of 0 between -1 and +2. There must be a root, as we call that. Especially for functions, if you're analyzing functions, finding where the function equals 0, so the roots, where the function intersects the x-axis, is very important, and we like that a lot. So it's very easy. So if you just find a point that's positive, a point that's negative, somewhere in between those, there is a 0. There is a 0. Which makes sense intuitively, obviously, right? But you need that basis of, well, it needs to be continuous and all that shit. And then this will be useful as well in the future for when we look at derivatives, because there's a similar two theories that are, it's like the intermediate. I think it's not called it, but well, it's not called the exact same. But yeah, you have basically the same theory, but for the derivative. But we'll talk about that next week or whenever. Inflections. What is inflections? What you mean by that, champ?
What do you mean?
But yeah. Limits. Limits are, you get closer to a point. To find a point, you can do lots of, you can make functions continuous with them by finding that point. You can find some interesting ones like the sine. You've got the squeeze theorem to find the limits if it can be difficult. You can take limits going to infinity. You can have limits resulting in infinity. You can have all kinds of crazy limits. And next week we'll talk about derivatives, which are, well, a derivative uses limits. Also, we'll talk about whatever the fuck Wheat is up to in the next week as well.
Who knows? Well, actually, it'll be what I was up to last week.
True.
Which I can't remember already, so it'll be good to get to.
Incredible.
It'll be, I guess, about the assignment I did. And I'll look at it or something. I don't know. I should probably check before then, so I actually have it in my mind.
Functions are okay. That makes sense.
Okay, so part of it is sorry, I need that.
We just call those critical points in Dutch, basically.
Is that what I need?
Champ. We'd call them
No.
Kritiekpunten, I think. It's been a while since I've actually done this. Function analysis. We used to have full-on like evaluations of this. We'd just get like 2 or functions or something, and we'd have to fully evaluate them in like into the second derivative or something. Which is quite fun. But it's also very important because things like derivatives are useful in physics because we use it all the time, because just the derivative of a position is its speed, derivative of speed is its acceleration, and this might be fun for some of you. The derivative of the acceleration is the jerk. There you go.
Nice.
Yeah. We'll talk about that next time.
My stuff for next time is some stuff about cosmic dynamics and a quick introduction to the Friedmann equations. I'm not going to say it's about the Friedmann equations because the week after that is literally called the Friedmann equations. So that's what I'll be doing tomorrow. And then for galactic astrophysics, we will have some little bit of stuff on galaxy formation and John or Jean's instability.
That wasn't fun for me. I got scared, actually. Oh.
Nice. Where are we going?
Where are we going? Well, I hope people... Because I feel like I talked a lot about limits there. I hope people actually kind of understand it. I hope that did help. Yeah, that'll be good. That'll be fun. Next week we'll get into derivatives, which is kind of hard. I'm scared. Where are we going? What is going? What doing?
I don't know.
Position, velocity, acceleration, jerk, snap, crackle, pop. Yeah. Which is just physicists giving them funny names, because, like, when the fuck do you ever use the crackle of a, like, when do you ever fucking need the crackle function? Yeah.
Crackle?
Like, jerk is almost never used, I feel like.
Anyway, options.
Options.
30, Amaria, Ratboy, Nyaran,
Ratboy.
Sean Bean,
Ratboy's
Overlight.
live? Is Ratboy live?
Yeah.
Am I blind? Where's Ratboy?
Yeah. You're
Where's
blind.
Ratboy?
And
I am blind.
Ratboy.
Ratboy's playing Overwatch. That's cool. Yeah, I was gonna say, I think it's like aircrafts use jerk, but that's all I've ever heard. Like, that's the only time I've ever like heard it used. Fuck me. Ratboy's playing Overwatch 2 because you
Ratboy's
can't play
playing
one.
Overwatch. Overlight is doing some shit.
Let's go to Ratboy. I
Labyrinth.
feel like Ratboy has been away for a long time and he's back, so it's good. Let's go, like, welcome him back.
Sure.
I guess. There you go. It started. Also, I don't know if you noticed, but
I didn't.
good. I don't know if you noticed, but I'm starting.
Oh, you mean Bingus?
Yeah, exactly.
Yeah.
We're starting to get. Slowly, we'll get more interesting, maybe.
Sure.
I was like, I don't
sure.
want my entire screen to be up, but, like, I've got the title up anyway, so I might as well. Like, I'm not gonna write anything in there anyway, so I might as well do it.
Of course.
Oh, we did. I wrote a lot today, which is good. We learned a lot.
Yeah.
I wrote 3
Everything's
things on
sorted.
your stuff, and then a lot on limits.
Look,
Well, you
that's
wrote
all I
way more
had.
on your stuff, so.
Yeah, exactly. Like, time-wise, we're about 50-50, so that's all that matters.
It's good.
Anyway,
Witch infestation.
I'm going to press raid now.
Okay, me too.
Bye.
Goodbye. Come back next week, same time. They didn't hear any of that.
No. No, of course they didn't.